ICRA 2025, I want to discuss one particular presentation by Yunzhu Li from Columbia University, and it's about physics-based versus learning-based modeling. I mean, this was one of the biggest conversations in the conference as a whole, and I want to use this presentation as a surrogate for a bigger topic, and that is, okay, if we have a line between physics, prior-based modeling or model-based control, or a sort of predefined world that we somehow define. Whether how we do that is a different question, but we have a predefined world, and then we have our systems move in that world, so model-based control, things along those lines. And on the other side, we have a fully learning-based or end-to-end learning, as we call it in the industry, where you don't use priors, you just learn. Now, our view here at Orange Capital Partners is that there is no such thing. We abide to the concept of any prior is just learning data in the sky. So whatever we learn and whatever we use is always has to be learned somehow. I mean, you can't just come up with stuff. You always need data to learn things. What you can do is maybe in order to gain sample efficiency, you can use priors. But priors always have a cost, and that is you bias the system. If let's say, for example, you use priors in the 1600s before Galileo for a flat Earth simulation of the world, you would have been totally wrong because you didn't actually take into account what Galileo taught us, and therefore you would have been wrong. So using that analogy, I just want to bring across this point that any prior we use, by definition, is going to limit our capacity for learning because we might be wrong. So that's number one. Number two, it takes away generalization capabilities because the prior, by definition, again, is going to limit generalization. If you do Lagrangian representation of a system, you're using Newtonian physics that probably will not be correct if you're going to Mars. So you're going to need general relativity for that. So again, like this whole conversation, which it was one of the bigger conversations at ICRA this year, is certainly not solved. And we here stand firm that we would like to see more learning-based models, just because generalization and data-driven learning is really what actually is going to drive progress. Now, this particular presentation is interesting because I think the way he lays it out is he gives us the sort of physics prior-based learning idea, then he gives us the fully end-to-end learning-based idea, and then he's sort of finding ways in the middle. He's talking about the necessity to have better priors for sample efficiency. And there's a difference between actual, practitioners in the field doing building engineering systems. I think, whether you're a humanoid robot company, or Tesla with FSD, they're going to have priors in there. They're going to have some predefined, experts or whatever you want to call mixture of experts, because they're going to have to make this work, right? You don't have the time and the resources to learn every single possible action that a car could take in Austin, Texas, prior to the launch of unsupervised robotaxi. So you're going to have some hard engineering in there. But in principle, you could learn everything end to end. Now, what's interesting in this presentation is the graph neural net representation, and I think that kind of really simplifies the problem. Like, if you take a piece of cloth and you use a graph neural net to represent that piece of cloth, you need three things. You need a definition of nodes, you need a definition of edges, and you need a definition of the messaging in between. Now, in material science, all of these things are called properties of the material. And what you can do is you represent the graph neural net. So you take that piece of cloth, you structure it with edges, edges and not nodes, but vertices and edges and messages. and then you learn from pixels what those represent, and you represent it in latent space. You might give it names. You can give it names like tension and friction, but you don't even have to give it names. All you care about is how does the system behave in, let's say, water? How does it behave with fire? How does it behave when it's being touched? And you could, in principle, again, learn that from, let's say, teleoperation or some sort of human-based initiative, and then use reinforcement learning to complete the learning process. I think this is sort of the way I see this going, the way we see this here, and that's the hope, that we can, by generating a lot of synthetic data from a prior, which is human teleoperated, or something like one-shot real, or from a ground truth, which requires very little data. We can bootstrap from there and then go and learn in simulation through reinforcement learning. I think he also mentions Nvidia Warp and DreamGen. Those are efforts by Nvidia to enable this type of learning. So Warp is sort of Python-based representation of physical systems. DreamGen is takes actual ground truth videos and then generates synthetic videos based on that with action-based models in it. So you can, let's say, take a piece of cloth, throw it in the water, and then generate thousands, if not millions, of generated videos with potential, further trajectories of that scene, and then use reinforcement learning to learn how to act, let's say, with a piece of cloth when it's wet. And of course, when you do that, you always have to sim to real problem. But overall, I think this is the path that we see this system going. I think that's probably the biggest conclusion of ICRA, in my opinion, is that we want to be further on the data-driven trajectory, because that's the bitter lesson that has been successful in the past. But we also want to strike a balance with engineering tasks that need to be solved right now, and they require, or they can be enabled with more priors. And I guess the holy grail is to have as little priors as possible, have as much end-to-end training as possible, while also delivering real value right now in order to start commercializing these projects, and also to start having a fleet of actual robots working in the field, so we can learn from those interactions and leverage those as priors for future reinforcement learning tasks. Thank you.